1 minute over.
Oh, I'm sorry, I have to be punctual. Because in the morning, 1 minute is very important.
Okay.
Yeah, morning.
It is still great to be here. Oh, I should stand up. It's still great to be here. Thank you for coming back for our second lecture. So last time, we talked about the groups that we are interested in. And we talked about this sister algebra of G, and we talked about its irreducible representations, which correspond to what we call the template representations, irreducible unitary representations of G. And so the goal of these lectures is to understand, maybe I should write it down here. Sorts of groups that we're dealing with are what are called real reductive groups. It means they're groups of matrices, Lie groups of matrices, almost connected and closed under the transpose operation. This is the crucial thing, closed under the matrix transpose operation. And we want to understand the representations. And this is a project which was already completed by Harish-Chandra in his famous work. And so I want to try and describe a perspective on the work of Harish-Chandra which is as geometric as possible. I wanted to maximize the amount of geometry and minimize the amount of analysis in the work of Harish-Chandra. And I forgot to say it last time, but the model for what I'm doing is the work of Joseph Bernstein. Here we go. So Bernstein treated the representation theory of reductive p-adic groups. So the field becomes a p-adic field instead of a field of real numbers. And so these were also studied by Harish-Chandra, but there's no doubt that Bernstein had the right perspective. Bernstein made a very beautiful geometric account of the theory of p-adic reductive groups. This work is very algebraic. It uses the fact that in this world of p-adic groups there are various very simple commutative rings around, finitely generated polynomial algebraic varieties. And in our world, these things do not exist, and we want to use C-star algebras as a substitute for ordinary commutative algebra. That's the idea. Anyway, so that leads to what's happening today. So we'll take a short break, a short holiday from groups and study just C-star algebras. The appropriate, or one of the two appropriate notions of modules of C-star algebras, C-star modules. And I want to construct, just for fun, I'll call it this thing, a category of non-commutative, just for fun, I'm calling it this funny name, topological spaces. Okay. So a lot of C-star algebra stuff. I hope at the end, and one more thing, I should suddenly add this to the list because it's kind of important. Say something about K-theory. K-theory organizes these C-star modules into a abelian group. And so we'll do all of these things, and if there's time at the end, we shall return to groups and illustrate some of these concepts using groups. That's the recipe today, for the business for today. We already discussed C-star algebras last time, because after all, we gave an example of a C-star algebra. But just for the record, to be complete, let's put the definition down. I said it last time, but now I can write it down. So these are examples of Banach algebras. They have to have an operation called complex Banach algebras, by the way. An involution operation. And I won't write down the axioms. I'll just say that they're attempting to emulate the operation of conjugate transpose on matrices, on square matrices. And there's only one other axiom. It's rather economical. And so people worried about C-star algebras back in the 1940s and the early 1950s, and they experimented with the axioms, and eventually they found that it all comes down to this rather beautiful formula. And this is a formula that's easy to check for the operator norm on matrices. So if you think of a matrix as a linear operator on this finite dimensional Hilbert space Cn, each matrix has a norm, and the operator norm has this property. Of course, you can do things infinite dimensional and talk about Hilbert space operators, and it's the same. So these things were invented by and Naiman in the 1940s. And eventually it turned out that with these axioms, it's possible to take A and faithfully, in fact isometrically, represent A as an algebra of Hilbert space operators in such a way that the adjoint operation becomes the usual adjoint operation on operators, conjugate transpose. So there are three big theorems and then a whole bunch of little theorems. The first theorem is every C-star algebra is isometrically and is star representative in the algebra of all bounded operators. Its usual adjoint operation on some suitably large Hilbert space. They proved this, at the time they had a less economical set of axioms, so it was easier to prove this theorem. But eventually it was discovered that some of the axioms were not needed, and so we have this very short list. They also proved very famously that every commutative C-star algebra is isometrically, I won't keep writing this down, star isomorphic. To the examples that you can easily think of, if you have a locally compact space, locally compact Hausdorff space, I'll keep writing that down there. Then the algebra of complex valued functions which decay at infinity, which means that for every epsilon there's a compact set, so that on the complement the function is less than epsilon in size. This becomes a C-star algebra, and the star operation is just, first of all, the multiplication is just pointwise multiplication, and the star operation is just complex conjugation, pointwise complex conjugation. And that's it. There aren't that many C-star algebras out there. They all look like that. You can compare this to what happens for Banach algebras. In Banach algebras in general, it's terrible because you can make a Banach algebra out of the 3 times continuously differentiable functions. You can make a Banach algebra out of bounded holomorphic functions on some open domain. You can make a Banach algebra out of holomorphic functions on some open domain which extend continuously to the boundary. You can make many other Banach algebras too. You can make L.1 algebras, which under a convolution multiplication. These are all legitimate Banach algebras. They're all different, and they're all very hard to understand. And they're all commutative, by the way, as well. But in C-star algebras, this is all that happens. It's very, very easy. Playing around with C-star algebras is very, very easy. It's like being a child. All the theorems you want to be true are true. It's just a much more elementary world than the world of Banach algebras. That's the point. And the other fundamental thing about C-star algebras, which was investigated by these fellows, and maybe I should add to the list another person who's instrumental in this whole thing, is Irving Siegel. Siegel, we mentioned this last time. Siegel is responsible for the invention of this C-star algebra G. And we'll see one small example of this in a little while. It's something called the GNS construction. You have a linear functional on a C-star algebra, and if it's connected to this wonderful star structure here in the following way, phi of A star A is always positive. You should think of A star A as being something like a positive semi-definite matrix. So if you have a linear functional which sends positive semi-definite objects to non-negative numbers, then you can do the following thing. You can build a bilinear form on A, a sesquilinear form on A, just by using phi. There's phi. It's like a Hilbert space in a product, except it could happen. I mean, this number is only bigger than or equal to 0. It's not necessarily positive if A is non-zero. So it's almost like an inner product, except there could be some vectors of length 0. But you can always, using the Cauchy-Schwarz inequality, form the quotient space by the vectors of length 0. The space of vectors of length 0 is a vector subspace, and when you divide by it, you get an inner product space, and when you complete, you get a Hilbert space. And this Hilbert space is related to A, so it stands to reason that A should act on this Hilbert space by left multiplication, and it does. And so you get from every state a representation. So it's a little bit interesting that the world of states, which is connected to Banach space theory, connected to the Hahn-Banach theorem, and so on, is related to the world of representations through this simple construction. If you have C-star algebras, then this is the general story. By now, there are quite a few books on C-star algebras, and there's a famous book of Dixmier, which I recommend. So Dixmier was very interested in representation theory, and he developed a lot of C-star algebra theory thinking about representation theory, but it never quite reached a conclusion. He never, after developing all of the C-star algebra theory, he never quite went back to representation theory to apply all of that C-star algebra theory. So that's what I'm trying to do. I'm trying to finish the work that Dixmier started by using C-star algebra theory more seriously to do some representation theory, like I say, inspired by Joseph Bernstein. Okay, so this is the elementary theory of C-star algebras. You can build representations. If you're in the commutative world, you might as well just think about topological spaces, locally compact spaces. C-star algebras, you could say, are some sort of non-commutative generalization of spaces. And all right. that these things all look like operators. So far, so good. Anyone concerned about that? Upset? You have a worry about C-star algebras? You should not have a worry about C-star algebras because C-star algebras are very easy. So Alain Kahn is fond of saying that people are stupid. They don't understand how easy C-star algebras are. So I'm telling you, C-star algebra is very, very easy. Of course, you can ask hard questions, difficult questions about C-star algebras, but at least the elementary theory is very, very easy. All right. Now let me talk about, so now that we have our rings sorted out, let me talk about modules. Of course, one natural class of modules are the representations of that is to say the maps. C-star algebra homomorphisms from A into bounded operators on a Hilbert space like this. And I'm going to inevitably get to mention this condition that it's always convenient to assume that the representation is non-degenerate, so that the zero homomorphism is not allowed, for example. We always want this sort of thing here. And when we're studying irreducible representations, the h pi is also not allowed to be zero. That's not, doesn't count as an irreducible representation. It's like saying 1 is not a prime number. It's a bad idea. 1 is a prime number, even though you can't factor it. Okie dokie. And then there are these things. Which I'll call C-star modules over A. So these fellows here are, if you like, let me not put that down. That's a bad idea. So let me tell you what these guys are. Let's give them a name. Let's just maybe write down the axioms. So first of all, these are complex finite spaces, not Hilbert spaces, typically. I want that to be, so conventionally people work with right modules in this context, so I want that to be a right A-module structure. And while we're at it, non-degeneracy assumption. So A is an algebra over C in the Hilbert space. Banach space here is a Banach space over C, and the two complex structures should be compatible, of course. And here's the key thing. There should be an inner product, an A-value inner product on E, bilinear in this sense, conjugate linear in the second slot. And then there are a bunch of axioms. And they're like the axioms for a Hilbert space. So the so it should be, first of all, complex bilinear. This bar taken into account. This means the conjugate complex multiplication structure. Which we call these factors B and W. So the inner product of B and W is not a complex number, it's an element of A, and so I can take its adjoint using the star operation, and I insist that the adjoint reverses the order of the inner products like this, so that's one axiom. I insist that the inner product of any V with itself is, as they say in C-star algebra, is positive. This means so the positive elements initially were described to be the sum of elements of the form A star A. But in fact, any element which is the sum of elements of the form A star A is individually the form A star A. So that's what positive means. And here I want it to be honest, an honest norm, honest in a product, if you like. And finally, if I take the norm in the C-star algebra of VV, this is just a norm. Sorry, it's a sort of C-star algebra version, or rather a C-star modular version of the basic C-star identity. I think that's it. I hope I have all the axioms. So these, you're supposed to think of this in the following way. If you're an algebraist, you're supposed to think of just representations as being arbitrary modules, and these guys down here as being projective modules. If you're a geometer, you should think of the guys on the top as being, I don't know, coherent sheaves, and the guys on the bottom as just being locally free, locally trivial. Okay. And let's just give some examples. So it took a while for people to understand that this was an important notion. And in the book of D3A, you will not see any Hilbert modules. But there's another book, which is quite nice, by Lance, which you can look at. So the fundamental example is this. Just take E to be A. Find the product of two elements in A. B. This, that does the job. If A is the complex numbers, then the axioms tell you that E is necessarily exactly the same thing as a Hilbert space. And to give you a more, I don't know, realistic example, this is close to the only, we'll look at examples coming from groups in a moment, but they all turn out to be very much similar to this. Suppose A is one of these commutative fellows, like in this theorem of Gelfand and Naimark. Suppose H is a Hilbert space. Then you can do the following thing. You can define E to be the functions on X, continuous, vanishing at infinity, values in H. And if you have two such functions, when you take their inner product, you're supposed to get a scalar function. And so that scalar function is supposed to evaluate P, and that's just the inner product in H, V1 of X. So that will do for now. This is by far the most illuminating example. You should always think about this example here. Think about A being a commutative C-star algebra and this being what a Hilbert module looks like. It's like a bundle over X. This is a bundle, the sections of a bundle over X, which is a trivial bundle. You can make the bundle non-trivial. Actually, the bundle doesn't have to even be locally trivial, but it almost does. You should think, even though it's not quite true, as Hilbert modules as being the modules of sections of locally trivial bundles, even though that's not quite the correct concept. Okay, so those are some examples. I need to say just a couple of words about operators on these modules. Or from one module to another, just a single module for now. We'll study only what are called the jointable operators, so from now on this will be taken for granted. That is to say, T will be a legitimate operator from our point of view, if and only if there exists another operator, S, so that this adjoint equation holds. So in other words, operators will always come in pairs. a T and an S, and of course we write S as the adjoint of T. So the only operators we shall consider will be, well, bounded operators, either after all a Banach space. Bounded operators T, for which there exists an operator S satisfying this adjoint equation. In the world of Hilbert spaces, it's a theorem that for every bounded operator T, S exists. But it's not true in Hilbert modules. You have to assume that S exists because there are some bounded A-linear operators which don't have adjoints. Okay, so that's not very complicated. And just like in the world of Hilbert spaces, the concept of compact operators is fundamental. The same is true here. So what is a compact operator in this context? Well, these are generated by operators of this form, just like we saw in the context of Hilbert space. I can build an operator in the following way. It sends x into the z or something. I can take the inner product of w with z, that's now a scalar, and I can use that scalar to multiply v on the right, because we're dealing with right modules, set that somewhere. And this gives a map from E to E. These things here are, if you like, the rank 1 operators. The general compact operator is a normal limit of finite linear combinations of these things. That's what a compact operator is. Just like in Hilbert space. And these operators satisfy a nice algebra, just like we saw before. For example, if you take V and it's a W star, you can ask, is it adjointable? Well, yeah. If you compose two operators of this form, you get a third operator of this form, given by a formula like the one I wrote down last. So in this most illustrative situation, E is the functions, Hilbert space valued functions on X. Then the set of all compact operators, which is written like this, K of E, first of all, it's a C-star algebra. Every operator in this collection has an adjoint, and that adjoint operator plus the operator norm makes this compact operators into a C-star algebra. And what it is just the functions from X into the compact operators on H, which are norm continuous and vanish in the norm at infinity. The algebra of all bounded adjointable operators is harder to describe than compact operators. Oh, in this situation, we've recovered the usual notion of Hilbert's compact operator. In this situation, maybe it's worth looking at in examples. In this situation, this is just isomorphic to A. Now acting by left. Those are Hilbert modules. And by the end of the lecture, I hope to explain what they're good for. So far, so good.
Do you need a
Yes, this condition here is a little exercise. This implies that it's T.
I mean, the inner product is not A.
Oh, did I not? Thank you very much. It's missing from my axioms. It's put in axiom 1.5. My apologies. Yeah, in all of the examples, the inner product is alinear, and I'm sorry, it's just missing from all of these forms. That's actually added to the collection. In the other slot, it's well, you can work out what happens in the other slot using this formula here. The A pulls out on the left and carries the stuff. My apologies. Good. What I was going to say. Oh, yeah, great. So what I want to focus on is not just modules, but for a moment, but bimodules. So I suppose I have a pair of C-star algebras now. If I have a pair of C-star algebras, I can study bimodules in the following way. First of all, I'll start off with a C-star module over B. And secondly, I'll assume that there's a homomorphism of C-star algebras from A into the compact operators on E. If I have such a homomorphism, then A, of course, now acts on E, and through this action homomorphism. And as usual, you assume that the action is not degenerate. That's it. I forgot to say, but maybe this is a reasonable place to do it. I was explaining how easy C-star algebras are, so let me just remark here a couple of things. That homomorphisms between C-star algebras that preserve the star operation are automatically continuous, in fact contracted. So the norm, what should we call it, alpha or something, norm of alpha of A, or plus the norm of A. And while we're at it, the range of such a homomorphism is automatically closed. So it's very, very nice how these things work. If a star homomorphism is injected, it's automatically isometric. This is beautiful. Okay, this is what correspondence is. And I hope by the end to show some interesting examples, but for the moment let's just leave this as a definition. And now I want to propose two correspondences. You should think of a correspondence as a sort of map from A to B. As I'll illustrate in an example in a little while. But if I have two such fellows, that's what we call them A mapping into the compact operators in E. Compact operators F. So the F here should be a C-star modulo of C. And E should be a C-star modulo over B, like that. And the first thing I can do is I can take the following tensor product, and it's just the completion. Maybe I should put that word in quotation marks. Of the algebraic balanced tensor. In fact, you just take the tensor product over C. In an inner product which is defined in the following way. So if I have a reasonable notation, V tensor W ponder this formula for just a moment. If I take two elements of the module E and take their inner product, then it will be something B. But F carries the left action of B, so I can multiply that thing of B against this W2 and get another action of F, element of F. And I can take their inner product, which is a C value inner product, and get something in C. When you do this, there may be some vectors, almost always there will be some vectors, whose length, so to speak, is 0. The inner product of that vector with itself is 0. By the Cauchy-Schwarz inequality, they form a subspace, in fact a submodule over C. You divide to form a quotient module, you have an inner product on that quotient module, and you complete, and you have a Hilbert module. And when you do that, A acts on the tensor product by the action just on the factor E. It's very easy when you have norms around. A lot of the norms hide a lot of difficulties in constructing these balanced tensor products. You just build a complex vector space, you divide out by the zero length vectors, and then you have the object. All right. So here's an interesting example. Suppose I have a star homomorphism, which we call it alpha, from A to B. Then I could define this EB just to be B. And the A, of course, acts on B through alpha. So A applied to an element of B is by definition alpha of A times B. That operator, alpha of B goes to alpha of A times B, is a compact operator, and so this defines a, as I mentioned before, this defines a correspondence. So does this. And now I can take their tensor product, as we were just discussing. What you get is C. Is the action of A via the obvious composition. So inside the world of correspondences, there are ordinary star homomorphisms, and this tensor product of correspondences corresponds to composition of homomorphisms. Just for color entertainment, let's call the resulting object, which is just on the verge of being obvious, the category of non-commutative spaces. So the objects are just C-star algebras. And the morphisms, well, isomorphisms. It's an obvious concept of isomorphism. Correspondences. To get an exact category. It's like, so it doesn't have any more objects than just the category of C-star algebras, but it has a few more morphisms, just a few more morphisms. And isomorphism in this category is what's called Morita equivalence of C-star algebras. So that's definition. There's already a notion of Morita equivalence, for example, for rings with units. Here let's call it C-star Morita equivalence. very interesting to work out what's going on in the case of commutative C-star algebras, spaces, in other words. And I won't go through all of the details, but it's not trivial at all to figure out exactly what these morphisms are in the case of commutative C-star algebras. They're very strange things. They, I have a morphism from, let's say, C of y to C of x. If we're talking about ordinary star homomorphisms, that's the same thing as a continuous map from x to y. But in this world of correspondences, it's not a continuous map from x to y anymore. A point of x is mapped not to a single point of y, but some finite number of distinct points in y, each of them attached to a vector space. And so the maps are rather interesting. They're maps from x into the so-called space of configurations of vector spaces on y. Very interesting what's going on. Morita equivalence, however, is kind of boring. It turns out that two commutative C-star algebras are Morita equivalent, just like in ring theory, if and only if they're isomorphic as commutative C-star algebras. But the morphisms are much more interesting. For example, I could build a correspondence from C of x to itself in a very interesting way. Maybe I'll just put in an example. Let's just take A equals B, just functions. And, let E just be the sections of a line bundle. Compact operators on E is just well, the only thing you can do with a line bundle. The only linear maps from the fibers of a line bundle to themselves are scalar multiplication. The only endomorphisms of a line bundle are just functions.
Your model, that example is basically the FC is a kind of a statistical regression analyzer.
I don't think so. Pleasure. So there's an obvious correspondence. I need a map from A into the compact operators on E, but A is C of x and the compact operators is C of x. So there's an obvious map. In other words, each line bundle gives correspondence. And it gives a distinct morphism in this category because E is not isomorphic to the trivial line bundle. It's equal to it, well, not necessarily isomorphic to the trivial line bundle if it's not a trivial line bundle. So this is a new morphism, in fact, a new automorphism of x. In this new category, spaces have automorphisms which don't move the points around. They're just given by line bundles. So there are lots of interesting things going on. However, we're on a mission to study groups, so we shan't spend too much time thinking about such things. But I mention this only to show that there are interesting automorphisms. In this category of instance spaces. But we don't want to get lost. We don't want to spend too much time in this category, even though it's a very beautiful and interesting thing. Where do we want to go instead? Let's not stray too far from representation theory. I have a couple of C-star algebras which are Morita equivalent. Then they have exactly the same representation theory. The categories of representations of A and B are equivalent. They have the same representations, same irreducible representations. Because you can use this tensor product idea, which is given right here. If I have a representation, let's say, of A with bounded operators on some Hilbert space phi, like this, I can build a representation of B. Maybe I should have started out with B. A representation of A now, I can build out of it. When you do this tensor product construction, it's not actually necessary for the definition of the tensor product that A acts as compact operators on E, or B acts as compact operators on F. You just need any old action by adjoinable operators. So you can apply exactly the same tensor product construction, whether or not B acts as compact operators on H pi and build a representation this way. However, if B acts as compact operators on H pi, it's easy to see that A acts as compact operators. That's an important remark to make, because remember I said last time that if I have a representation which acts as compact operators, it's always a discrete direct sum of possibly infinitely many irreducible representations. Representations which act as compact operators are completely decomposable without using any fancy continuous decompositions in the spirit of von Neumann's theory of phenomena algebras. And this correspondence here preserves those types of completely decomposable representations, the ones where the C-star algebra acts as compact operators. So this is an equivalence of categories. If this is irreducible, of course, to go back, you just tensor with F. And so equivalent C-star algebras have exactly the same irreducible representations. That's why we're interested in them, because we're trying to study irreducible representations. How do we do that? So, this is potentially interesting for us from the point of view of representation. I think I'll permute the order of my plans here. I think I'll now discuss some fairly substantial example from representation theory. I also want to discuss K-theory, Fredholm operators, but let's take a break from all of these definitions to work out a non-trivial, a very non-trivial example of illustrating some of these ideas. Any more questions, Thomas?
No.
Any mistakes?
No.
No. Look more carefully. Do you like candy? You know, chocolate? How do you say candy in Japanese? Chocolate, sweets for children?
Same.
Candy. Candy. Yeah? Kit Kat, this type of thing. You like? Yeah? You like? You like?
Yes.
Kit Kat? That's good. Okay. Each question, from now on, if you say a good question, then you get a prize. Get a prize, one candy bar for each good question. So I owe you one candy bar, one Kit Kat for you. Okay? So encourage you. If you ask a good question and you're a student, one candy bar. I have to go buy some. I don't have any. So you pay attention. Oh yeah, here's a. So far we just made some definitions, and it's kind of an incredible thing that these definitions alone tell us, they almost tell us something very, very interesting. Something very interesting about the representation theory of this group. We need one geometric theorem, which we'll discuss next time. But it's already interesting to see what happens with this example. So here's a group. Of course, there is a reduced C-star algebra attached to it. We're interested in studying the representations of this group. And how are we going to do it? Well, here's a topological space. I want to take every point in the plane apart from 0. Now, if I have the plane is just the standard two-dimensional vector space, and these are 2 by 2 matrices. So each matrix can be multiplied against any vector in this space, and I get another vector. Okay? So there's a map from an action just by what's called matrix multiplication on vectors. Nothing fancy, I mean exactly what they said. Is it right? I think it's right. And so in this way, x just becomes g modulo n. And this subgroup. This is just the isotropic group. And the action is transitive. You can always multiply any vector to any other vector by an SL2 matrix, as long as the vectors are 0. Okay, very easy stuff. We're not done with the symmetries of this space because there's also an action of the group of non-zero numbers. Sorry for all of these x's. This just means the non-zero reals. Just by scale multiplication. And the first action is through linear operators, so they commute with scalar multiplication. These two actions commute with one another. And this is part of a general story. If I have a non-zero number, I can make it into a determinate 1 matrix. Obvious way. Let's call this group L. It's what's in reductive groups is called a Levy factor, and it's called a unipotent subgroup, standard unipotent subgroup. And anyway, L acts on space G modulo n on the right. It acts on the right because L normalizes n. If you take something, an n matrix, and you conjugate it by an L matrix, you get another n matrix. So there's a right action of L on the cosets. This. L sends me a matrix here. L has an inverse. Sends this coordinate to G. That's a well-defined right action. And that's what's going on. Anyway, here's a little geometric story. So we built a representation. We built a representation of G as bounded operators on L2 of x through this group action. Actually, there are a couple of small points to worry about here. The first is very elementary, that G preserves Lebesgue measure. So the natural action on the Hilbert space coming from the action of G on X is a unitary action of G on this Hilbert space. On the other hand, L doesn't, but we can adjust. Whenever you have a homeomorphism of the space, it doesn't preserve a measure. You can still get a unitary operator on L2 of X by adjusting by some radon derivative. To get unitary action. The most significant thing to worry about is that these representations really are template. In other words, they correspond to representations of the reduced C-star algebra. There's a difference. Not every representation of unitary representation of G corresponds to a representation of the reduced C-star algebra. There was this weird abstract maximal C-star algebra that you mentioned. But here we're talking about representations of the reduced C-star algebra. So you have to check that this is really well defined, that the obvious formula gives a bounded representation of the C-star algebra. Which we'll do, but not today, because I don't want to focus on that. So I make an assertion, which is that the natural actions of SL2R on X and of the non-zero reals on X give rise to actions of the C-star algebras of G and L, the reduced C-star algebras, on this space. You need to check a little stuff, no big deal. We'll come back to that later. So far, no Hilbert modules, okay? And indeed, that's because we're not exactly looking at the right thing here. This is not an irreducible representation, by the way. It's not irreducible because, according to Schurzlever, irreducible representations have no operators other than the identity operator, which commute with the representations. On the other hand, here, the actions of C star of G and C star of L are the same. Commute with one another. So there are many, many operators which commute with the action, the left action of C star of G, and so this left action is not an irreducible representation. Okay, fine, you say, let's decompose L2 of X into a family of irreducible representations. Well, it's not so easy, because when you do that decomposition, you find that you are in the world of von Neumann, and you need to understand the concept of a continuous decomposition into irreducible representations. It's very complicated what goes on. So let me show you how Hilbert modules come to the rescue there. Let's go over here. Our project in these lectures is to understand the irreducible representations of this C star algebra, because they correspond to Harish-Chandra's tempered representations of G. And it's a beautiful and interesting story that Harish-Chandra discovered. So I want to tell it again. We want to understand it better. And this representation is not irreducible, but we hope to be able to use it anyway. So here's some very simple geometric facts. So here's this group of non-zero real numbers. Decided to call it L. it's a proper action. So dynamically speaking, it's a completely elementary action. So what this means is that if I look at the map from L times X, X times X, which sends L and an X to, well, I guess it's a right action. Maybe I should have written it the other way. This is unnecessary. Tidy, let's do it this way. This is a proper map of space, the inverse image of a compact surface pattern. After all, if you take the plane and you remove the origin, then topologically this is just a circle times a line. And the way this group L is acting is it's basically just translating along the line. It's a very, very simple, very, very, very simple action. Nothing like orbits winding around in a complicated way. The orbit structure is very, very elementary. That comes to the next fact, which is the quotient space. Well, the fact that it's proper tells us that this is a decent space. It's Hausdorff. But it's also a compact topological space. Think about it. Canonically identifies with projected line. I guess you don't have to think about it at all. That's the definition of V1. So that's very, very simple. But here's some interesting consequences in the world of functional analysis. We can start to build a more interesting inner product now on this space, which is valued in the convolution algebra of functions on L, not in scalars. And you use the following formula. So what is this thing? This inner product is supposed to be not a scalar, but a function. And so in order to tell you what it is, I have to tell you what the value of this function is at some element L. And here's what I'll do. I'll just take F1, and I want to take the ordinary inner product, put it here, in the sense of Hilbert space. But I want to take the inner product of F1 not with F2, but with a translation. Actually, the good formula is L inverse. I memorized this beforehand to know it should be inverse. As L varies, as L goes to infinity in the locally compact group big L, these functions, F1 and F2 translated by L, eventually they have disjoint supports, thanks to the properness of this action. Proper means that if you have any compact set and you start to translate it using the group action, the translation of that compact set will be eventually disjoint from the compact set you started with. And so when you form this L2 inner product, you'll get 0. So this thing here is actually a compactly supported function. You wouldn't get a compactly supported function if the action was not proper. But here you do. And now you can complete in the standard way that I've been mentioning more than once, basically the way of Gelfand, Naimark, and Siegel. Get what you might call C-star reduced of X. Now X is just a space, it's not a group, so this C-star of X is not a C-star algebra, but it's a C-star module over C-star. So here's the first consequence. Coming from this, on the other hand, the quotient is compact. So there's a left action of this C-star algebra on X coming from left action of this C-star algebra on this module, coming from the action of G on X, up there, you have to check. You have to check that, that the action is through bounded operators. There's some small detail to worry about, which I mentioned somewhere here. Yeah. But it's okay. We'll talk about that later. What I want to focus on right now is this action is by compact operators. So we have one of these correspondences. Two C-star algebras. This one, which at this moment is mysterious, we want to understand this C-star algebra. We want to understand its irreducible representations. And this one here, which, as I'll mention in just a moment, is not mysterious. Oh, yeah, said Roger correctly. And we do understand its irreducible representations. I'll tell you just about this in just a moment. And we want to use this correspondence to tell us something about this mysterious. Suppose I have any module with C-star type. Over any A. Make a very general statement here, elementary general statement, then we'll go back and apply it. Okay, I need one small hypothesis here, which is that if I look at the set of all possible inner products, make it into a linear space, take the linear span of all possible inner products, this is a subset of A, and let me assume that the set of all possible inner products is all of A, so the modular C is all of A. The thing I've written on the left is definitely an ideal, a closed two-sided invariant under the star operation ideal inside of A, but let's assume it's all of A. Otherwise, we replace A by that ideal. Then the compact operators on E is Morita equivalent, in other words, isomorphic in the category of non-commutative spaces, just E. Here's why. There's a sort of obvious correspondence in the compact operators to A, by definition. That's a morphism in the category of non-commutative spaces, going from the compact operators to A. What about the other direction? Well, you can do the following thing. It's kind of interesting. You can take E and form what you might call E star. What by E star I just mean the complex conjugate Banach space. But now I'm going to give it an inner product valued not in A, but valued in the compact operators. I have a V star, W star, and I want to, I'm going to build a fancy inner product here, which is not valued in A, it's valued in the compact operators, and I do just about the most obvious possible thing, namely this. Here's one of these rank 1 operators, and So there's formally there was a right action of A on E. When you take the left action, you can define when you take the E star, you can define a left action of A on E star in more or less the obvious way. A acting on a vector D star, we'll just define that to be B acted on by A star. So each time I have a correspondence, I can reverse it in exactly the way, sorry, each time I have a Hilbert module, I can reverse this sort of obvious correspondence to get another correspondence like this. And now you check, you do the calculation, these two correspondences are mutual inverses to one another in the category of non-commutative spaces. So the representations of this C-star algebra are exactly the same as the representations of this C-star algebra. And the map is sort of standard color. It sends H pi to E constant over A, H pi is an equivalence. Start this way here. From the category of representations of A, category of representations. And nearly done. We're about to say something interesting, so please stay awake because something good is about to happen. Here's a little lemma. I don't know who this is due to. It's maybe ancient, but you can certainly find it in Dixon's book. It's typical of the sort of machinery that was developed in C-star algebras for representation theory, but then not used so much. But here's what it says. Suppose I have two C-star algebras. Let me call them C and D. And suppose one is a subalgebra of the other. It tells us where to look for to find the irreducible representations of C. Every irreducible representation of C is a sub-representation of an irreducible representation. If I have a representation of D, of course I can restrict it to C, and now I get a representation of C. And it may not be irreducible. After you do the restriction, it may not be irreducible anymore. But what happens is that among the irreducible constituents, you will find all, in this way, all of the irreducible representations. And the proof is just one of these functional analysis arguments, very abstract, so the proof cannot be that hard. It uses the Hahn-Banach theorem, it uses some theory of extreme points. Remember we talked about positive linear functionals a while back. It turns out that extreme points in the convex set of positive linear functionals correspond to irreducible representations through the JNS construction. So you need to understand something about extreme states, as they're called, and then finally, the connection between linear functionals and representations is through this JNS construction. So it's very elementary, very abstract, not very boring if you like, but there it is. Now, going back to our situation, there's an obvious map. We have an action of C star of G on this Hilbert module, a star homomorphism from here to here, and so an obvious surjection like this. This action map may have some kernel. In fact, it does have a kernel. There's some ideal, but after you divide out by the ideal, this C star algebra becomes isomorphic to this one. And obviously, this sits inside of which is Morita equivalent, as we just pointed out, to C star L. Now, L was an abelian group. It was a long time since we started this example, but L was the group of diagonal matrices, diagonal 2x2 determinant 1 matrices. So by Fourier theory, this is just the equal to the functions on the Pontryagin dual of this abelian group, which is just what it. R cross is just R times Z mod 2, and the Pontryagin dual of that is just Z mod 2 Z. So it's very, very explicit what's going on. And the irreducible representations of this is just functions on this space. As I mentioned, are just given in the first lecture just by evaluation at points. So the irreducible representations of this C star algebra are totally under control. We know exactly what they are. They correspond to characters of this abelian group L, and they are just listed by elements in this topological space. That tells us what the irreducible representations of this C star algebra are. As for the irreducible representations of this C star algebra, we don't know, except to say that each irreducible representation of this C star algebra sits inside of an irreducible representation coming from this construction here. Okay. And so we get a very concrete collection of representations of G in this way. Starting from the fairly standard action of SL2R on vectors. Go back to the representations of the C star algebra. We don't really know what it is. It's quite easy to calculate, but at the moment it's just some abstract C star algebra. But we can say some things about it, namely the irreducible representations are labeled by points in this space, and the labeling is given in this way. The other thing we can say is that these actions are actions through compact operators. That's a general feature, as I mentioned, of these Morita equivalences. And so it's completely decomposable. When you restrict to this. Keep writing this whole thing out. In fact, what happens is that in every example except for one, the representation remains irreducible when you do the restriction. And only in one example is the representation decomposable, and then it only decomposes into 2 bits. So it's basically the restriction of irreducible is again irreducible. And so we get the continuous series that I was mentioning. Continuous series N. they're labeled by non-zero real numbers, and the labeling is almost always perfect. That is to say, you can understand the representation, characterize the representation by its label, except for one time when the same label is used on two representations. So the limits of discrete series. I said that the dual of any C-star algebra is a topological space, and the topology comes from closed ideals, and there's a closed ideal floating around here, which is just the kernel of this map from C-star of G to the compact operators. And what I've described almost completely is a certain closed subset of the tempered dual. The only subtle issue is the labeling. How decomposable are these representations? And more or less, not exactly. This divides the problem of understanding a representation theory into two bits, and now we only have to understand the complement. And the complement corresponds to the discrete series, and I'll explain next time how we can understand that complement in a very concrete way using my current favorite picture. I mentioned this before, a better version of it. I mentioned this picture last time. Here. What I've drawn here is basically the plane with the origin removed. This is a right circular cone. Just remove the origin here. So this is what you get by taking the plane with the origin removed and dividing it out by identifying a vector with minus the vector. And inside of it, there's a copy of a hyperbolic plane, like that. So it doesn't look very hyperbolic, negatively curved if you draw it like this, but in the this whole picture is taking place in R3, and if you restrict, so if you put the 2 on the Lorentzian metric in R3, then the restriction to this curve is, to this surface is hyperbolic. I'll explain next time how this mysterious picture that I was trumpeting, that I was promoting last time, allows you to understand this complement. If we had not gone through all of this bother, then we'd be in trouble because we'd not be able to usefully use, is it still on the board? Yeah, this teaching is young. Because the representations of the algebra of bounded operators on a Hilbert space, this would be the proxy for our compact operator algebra. We wouldn't have this object anymore. If we did not define this C-star module, we would not be able to calculate with this object. And the other alternative would be to use the C-star algebra of all bounded operators here. This action is not through the compact operators on this Hilbert space, it's just on bounded operators. And the representation theory of the bounded operators is terrible. This is a completely intractable problem to understand the representations of the C-star algebra of all bounded operators. So this lemma would tell you nothing useful whatsoever, because you would not have such a Marucha equivalence, you would be nowhere. But by means of a small investment in this C-star module technology, using, if you like, projective modules at the appropriate point, and not arbitrary modules, you've broken up the problem of understanding the tempered dual into two parts, and one part, the problem of understanding the continuous component, is almost completely solved. It's almost over. Okay, there's a small problem in understanding these decompositions, but let's just call it small and worry about it later. And And then there's the part of understanding its complement, which we'll talk about next week. With the language of Hilbert C-star modules, with this language, with the elementary C-star algebra ideals, you can make tremendous progress towards understanding the rough shape of the representation theory of a group like L.2, using only extremely elementary geometry. It's disappeared now, but this whole discussion relied only on two extremely elementary facts. Namely, one was that the group L of scalar factors acted properly on the plane, take away the origin. And the other was that the quotient space was compact. Extremely elementary geometry allows us to break up the dual into two easy pieces, or two pieces, one of which is very, very easy to understand. It's just over as far as the continuous series is concerned, using totally elementary geometry, the fact that some action is proper and co-compact. As for the other, this picture will be involved, which I keep amusing you with, and so we'll discuss that next time. So you make a small investment to learn what a Hilbert module is, this funny category of non-commutative spaces. You make a small investment in these silly ideas, and immediately you see some clarity. Immediately, boom, you understand what's going on for half of the representation theory, just like that, for L2. There are no crazy representations of this algebra. All right, so I think this is, even though it's extremely elementary, I think these are important points. I hope it tells you something about the value of this concept of C-star module. Now let me show you just one more thing. Any questions? Remember, prize. Kit Kat. No? Okay. Nobody's hungry. Okay, I have to eat all of those candy bars myself. I don't know. It'd be bad for my figure. The language of C-star modules and compact operators is useful for these very elementary considerations. Now I want to show you another reason why this language is very, very useful for us, which is on the face of it completely different. I want to do now something completely different. It's over here. So the last topic for today. How we get. Of course, there will be a connection in the end. Suppose I have, again, the C-star algebra. And C-star module of this C-star algebra. Actually, let me, suppose I have a couple of them. We're only interested in these adjointable operators. So I must say it. Suppose I have some operator, let's call it T. It goes from one of these spaces to the other. I want to take the idea of Fredholm operator from the Mbonic space theory, which means that the co-kernel and the kernel of the operator are finite dimensional, and carry it to this world, say that this guy here is Fredholm. Well, I don't want to be studying the kernel and the co-kernel, that would be a bad idea. But this is an equivalent formulation of Fredholm, which is perfect for carrying over. It's an invertible modulo compact operators. We already have a notion of compact operators. So in other words, there should exist an operator going in the reverse direction. so that if I look at these compositions here, these are compact operators in the sense that we've been discussing. In the world of Hilbert spaces, in other words, in the context where A is equal to the C-square algebra of complex numbers, this is the usual notion of Fredholm operator. So over C, each such operator has an index, which is the dimension of the kernel T minus the dimension of co-kernel T. It's an integer. These operators have discrete invariants of this type. And we want to do something similar here. And that's the context of this definition. So K0 of A is just comes out to be a set, in fact a group of homotopy classes. Fredholm operators. Over A, in the sense of the definition above. This is a very beautiful approach to K theory. Worked out like an edit as well. I need to tell you what homotopy is. It's something very, very easy. A homotopy of Fredholm operators is just the same thing as a Fredholm operator over not the C-star algebra A, but the C-star algebra functions from the interval over A from the interval to A, like that. And in order to make the definition sensible, suppose I have such a fellow. And suppose E0 and E1 are modules over this algebra of functions with values in A. We can use our friend, the tensor product operation, to push these modules forward, just like you can with projective modules. Push them forward from this algebra to the algebra A itself. So what I can do is tensor here with evaluation at any point x 0, 1. A is a C-star module over A, I already explained that. But A also carries a left action of this algebra of functions, because I can just pick any point in 0, 1 and evaluate at that point to get a left action of this algebra of functions on A itself. And if I choose a fixed x for a moment, I can convert any homotopy, in this sense, to just a single operator. So this is now a Fredholm operator between A modules. So modules over A. have a single Fredholm operator of this type over this function algebra, I can, so to speak, evaluate it, take its fiber over any point in the unit interval, and obtain a Fredholm operator of Hilbert C star A modules of this type. And as I vary x, I get a family of operators. That's what a homotopy is. So I'll say that two Fredholm operators are homotopic if they're isomorphic to, in the obvious sense, unitarily equivalent to endpoints of the family obtained in this way. It's a very beautiful and economical definition, very abstract, but it defines K-theory in terms of homotopy classes of Fredholm operators. Kasparov was inspired by a beautiful approach to K-theory worked out by Pugh, which he needed when he was studying the index theorem for families of operators with sigma. It was also worked out by the same theorem as proved by Yannick. There's such a thing as K-theory of a locally compact space, and when A is the algebra of functions on a locally compact space, this is a Pugh-Hissebrecht K-theory of a locally compact space. But you can define it very elegantly and economically using the language of Hilbert modules, the C-star modules, and tensor products. It's very, very beautiful. Here's an amazing exercise, just the most amazing exercise. Put this here. I did this exercise at some early point when I was a graduate student, and you know, sometimes you learn a mathematical fact and it changes your life. It just changes your way of thinking about some entire mathematical subject. And here's I strongly recommend this exercise. Suppose you have an actual invertible operator. Between C-star modules over A. Now, an invertible operator is certainly Fredholm, because if T is invertible, then there's an S, so that the compositions minus 1 are not just compact operators, they are 0. That's what invertible means. And so invertible certainly implies Fredholm. Of course, an invertible operator is boring from the point of view of index theory. The index of an invertible operator is 0. And the same thing is true here. This is just spectacular. There's a trivial construction, which I won't show you because it's an exercise. T is homotopic through Fredholm operators in the sense of that definition over there to the 0. The 0 operator between 0 Fredholm modules, between 0 C-star modules. The 0 operator from 0 to 0, it's not much of an operator, but if you check the definitions, in fact, it is a Fredholm operator. It's a Fredholm operator. Not a very interesting Fredholm operator, but it is a Fredholm operator. And it's homotopic to any invertible T. It's kind of an amazing thing. Oh, one more exercise. You may say, good heavens, if you can just homotope things away like that, maybe Kasparov just defined the 0 group. Good. So I guess another exercise is that to praise the complex numbers, then T1 T is homotopic to another operator, T prime, through fret line, T prime. If and only the index of T. So in the case where A is complex numbers, this space of homotopy classes is actually the group C, the additive group of integers. There is a natural addition operation here, by the way, which you get by just taking direct sums of operators, direct sums of Hilbert modules and so on. There's also an additive inverse operator, which you get by replacing any operator T by its adjoint T star going in the other direction. So the space of the thing that Kasparov defined is always known to be an abelian group. This abelian group does not see invertible operators, which we think is appropriate because invertible operators should have no index theory. And in the simplest case, it gives you the right answer. If A is the continuous algebra, the algebra of continuous functions on a point, then what you get here is the K-theory of the point. You get something non-true. It's beautiful what Kasparov did, and as far as definitions go, it's just over. Once you've absorbed the language of Hilbert modules, you've successfully defined, in this way, K-theory.
Oh, excuse me.
Yeah.
Can you explain the definition of homotopy again? So suppose you have two Fredholm operators, say E0 to E1 and E0 prime to E1 prime. Then how can you tell their homotopy?
I will answer your question. So let me say in more detail. What's going on here? So a homotopy is by definition such a thing. This is what a homotopy is. Now I need to describe what it means for two operators to be homotopic.
Yeah.
And so let me just spell that out. So suppose I have something like this. So the condition is that there should exist a homotopy like this, and there exists isometric isomorphisms, unitary isomorphisms. Let's call them too many zeros and ones. Too many, I'm not going to give them names. So here we'll tensor its evaluation. 0. Decided not to do that. It's not. I'm trying to build 4. I want to assume the existence of 4 unitary isomorphisms. And I'm going to write them down.
On the board, on the right hand side, probably evaluation at 0.
Yeah.
Left and then A instead of C of 0 and A or something like that.
Yeah. Let me write this down properly here. So we should also like to evaluate at 1, same thing. Now we want to go to E1 prime. Oh. Since it's not double prime, there we go.
I guess the A, you should replace A with C of 0, 1, A. Otherwise, the evaluation doesn't make sense.
Yeah, no, this is a module, the right module, over this ring.
Yeah.
On the other hand, A is a left module over this ring by evaluation at any particular point
Left
x.
module. Okay.
So this is a balanced tensor product over this algebra, and the way in which A becomes a left module depends on a point x in the interval. So I only wrote down that x. So So this is a tensor product over the algebra of functions, where the A becomes a left module through evaluation at X. And the same thing here. And what you're positing is that there exist four such fellows. What's very confusing about this, and I apologize, is that the symbols 0 and 1 are doing too many things. 0 and 1 are being used too many times in the same definition, so I apologize for that. Anyway, once you have these isomorphisms, you're in business. Between, let's get it right, between these two modules here, we have the operator T tensor the identity. Between these modules here, we have T prime. And between these two modules, we have T tensor the identity. Here we have T. So there should exist such four isomorphisms so that these diagrams commute. Oof. Great.
So that it's a family of homomorphic depending on X. So that
Yeah. The reason I put in an X here is I wanted to give you the impression that there is some sort of continuous family of Fredholm operators over A. And in this continuous family, when you set the parameter X equal to 1, you should get the T double prime, and when you set it equal to 0, you should get T prime. And the only question is, what does it mean to get such an operator? It means there should be commutative diagrams like this. So, finally, it's done. I think it's now a complete definition. And it would have been much clearer had I chosen better notation. I want to, let me say, I guess I should give one more example here. I forgot to mention this, but if you come from algebra, then you may be accustomed to thinking that all rings should have a multiplicative identity. But in our world of C-star algebras, C-star algebras do not necessarily have a multiplicative identity, a unit element. For example, the C-star algebra of a group, if the group is not discrete, does not have a unit element. When it does have a unit element, C-star algebra is, say, unital. It means there's a multiplicative identity element. Anyway, if you have such a thing, and if you have two C-star modules, suppose that they're finitely generated and projected just as modules. I mean, just in pure algebraic sense. So they're direct sum ends of finite numbers of copies of A plus A plus A plus A plus A, each of them. Now, there's always one canonical operator from E0 to E1, namely the 0 operator. And this fellow here is present. Let's make it another exercise. So if I have a pair of projective modules, or just one projective module and the other one is 0, whatever you like, then it becomes a Fredholm operator, and so it determines a K-theory class. So each projective module, indeed each formal difference of projective modules, gives rise to a K-theory class. And indeed, it is the case, just a little remark. If you know what this means, if A is unital, then this object that I just built using Fredholm operators, the brilliant definition of Kasparov, which you may hate it if you're an algebraist, but this turns out just to be what the algebraists would call K0. The zeroth algebraic K-theory group of A. So it's something which is at the same time very algebraic and it's a very index theoretic. It's two personalities. And we're running out of time, so let me just try and bring things together. I don't have time to give all the details. We'll do that another time. Let me say something. So this is, if you like, just a short introduction to try and bring everything together. Suppose G is one of the groups that we're interested in. For example, SL2R, that's an extremely interesting example. An extremely interesting example for this problem. Suppose G is a real reductive group. For simplicity, I want to assume that G is connected. And for simplicity, I want to assume some other things. I won't discuss non-connected groups, but I will discuss these other hypotheses later. The first is that when I take G and divide it by K, which is the orthogonal matrices inside of G, I form this homogeneous space, which is a manifold. Let me insist that this is even dimensional. If I take SL2R and divide it by the orthogonal matrices in SL2R, that's SO2. SL2R has 3 dimensions, and SO2 has 1 dimension, and 3 minus 1 is 2. It's also true that 3 minus 2 is 1, but the relevant formula is 3 minus 1 is 2. So this is okay for SL2. And there's an additional condition, which is related to the double cover of the orthogonal group. I'll just say the spin condition is satisfied. Now, there are a couple of things you could do. One is to, there are 2 groups on the board. There's G and there's K, and we could study the K theory of G. Excuse me, we could study the K theory of the C-star algebra of G, or we could study the K theory of the C-star algebra of K. It happens to be the case that the K theory of the C-star algebra of K is easy to calculate. And it's equal to what the representation theorists call the representation ring of K. And of course, there's the C-star algebra of G. And there's a sort of map here, which is defined using Fredholm operators, which is the reason that I discussed Fredholm operators. But you should think of it as a sort of induction operation, which takes representations of K and converts them into representations of G. And so this is an operation which is a little subtle. obviously this map turns out to be an isomorphism. I showed you what the C-star algebra of SL2R looks like. I showed you what it looked like last time, and we had more discussion of it again today. There's a continuous part and a discrete part, and it turns out that both of them contribute to K-theory over here. And it begins to look a little bit complicated, and the bigger the group is, the more different parts there are, and it becomes complicated to understand how to do the organizing, to organize the representations. If you look in the papers of Knapp and Zuckerman, which are the papers where the classification of the tempered dual was finally finished, it was started by Harris-Chandra and it was finished by Knapp and Zuckerman. If you look at the final result, it's very, very complicated. It's very complicated. We'll discuss what it looks like in later lectures, but it's very complicated. On the other hand, there is a statement here which can be verified by looking at that complicated classification. And the statement is extremely simple. There's some natural operation here which it may look intimidating, but it's a natural counterpart of an idea of Bott's from the theory of Bott-Barrel-Way theorem. It's a very natural map, and it takes something which is very, very easy, thanks to the work of Hermann Weyl and relates it to something which is in principle very, very complicated. No, this is not complicated. It's as simple as this thing is here. This is one of a very small number of statements you can make about representations, the tempered dual, which is just elementary and beautiful and simple and universal. I made some assumptions about G, which I needed just to write down a simple version of this map. But it's easy to remove these assumptions, and then the corresponding version is not much more complicated, and it's always true. In fact, the group doesn't even have to be reductive. Any Lie group at all in the whole world has a corresponding isomorphism statement like this. This is some universal truth about how the reduced C-star algebra of G, how tempered representations of groups organize themselves. And it's true in an unparalleled degree of generality. It works for nilpotent groups, it works for reductive groups, it works for solvable groups, it works for combinations of those. It's something which is very mysterious, not in terms of the transparency of its statement, but in terms of the scope of its effect. There's nothing like it in representation theory. No statement which is as universal as that. So I want to describe a bit more about this sometime, maybe not next time. And as we start to do representation theory and go back to our picture of the cone and so on, we'll learn more about the C-star algebra. And as we're going along, we'll see how it corresponds to this strange K-theory statement here. So I'm sorry for the last 10 minutes. It's a little rough. Just think of it as an appetizer, something to suggest that there are interesting problems relating K-theory to C-star algebras. Good, we'll stop here. 1 minute early. So since we started 2 minutes early, oh no, now 1 minute early, so I talked for exactly 120 minutes.
Any question, comment?
You have a condition for the K? Like the couple K?
No,
Exist such K or not?
it's a fact that every Lie group, whether or not it's reductive, whether or not it's connected, as long as it has only finitely many components. Any Lie group, subject only having a finite number of components, always has a maximal compact subgroup which is unique up to conjugacy. There's always a K unique up to conjugacy, and that's the K which appears here. There are, of course, now 2 Ks on the board. There's nothing to be done about this.